how's the guy doing?
Okay, so let's talk forces a little bit. How does, now I want you to think back here. I want you to think back to the demonstration that we were working through in class. What, did we finish that last Monday?
No, we finished it
The
like
Friday prior to that,
Friday.
right? Okay, so it's been a while, like a week and a half. But remember what we did with this. Now let me just refresh your thinking. So what we had a cart and we had a bunch of masses piled on the cart. That's how we finally ended up doing this, right? We had a couple kind of trial runs and got good stuff, but eventually we figured out the best way to do this one. Put a bunch of masses on here, take a mass off of the cart, suspend it from the pulley, right? And then that moved the cart, right? Okay, what did we see? We had a graph, right? What did that graph, well, before we even get into the graphic part, just kind of broadly speaking, what did we find about how acceleration and force are related?
Force equals mass times acceleration.
Well, that's okay. If we want to get very specific, we found force equals mass times acceleration. On kind of a broader level, didn't we find that increase the force, increase the acceleration, right? And this was pretty cool. We found that if we graphed, I can't remember which, I think we had F up here, right? We had A right there. If we graphed the points that, the data points that we got for force and corresponding acceleration, right? Remember that? What kind of pattern did they form?
Linear.
It was linear, wasn't it? It looked kind of like, might have been a little bit off, but basically, it was a line through the origin, right? That's significant. What's that tell us? Force and acceleration are what? What's the word that we can always use to describe a relationship, a linear relationship through the origin between two quantities? What is it again? They're proportional, exactly. Force and acceleration are proportional. Yeah. We found that, yeah, and that's, I mean, and really as a physics teacher, that's really fun to be able to see that happen. We have such good equipment, we can actually see it happen, because back in the old days, it never quite, we'd have to kind of say, well, if it worked right, this is what we'd see, but we actually get to see it with our good equipment. So, yeah, so these are proportional. Now, we know that if two quantities are proportional, well, we write that like this, right? We say F is proportional to A. That's interesting, but it's much better if we can write it in the form of an equation, right? And what does a proportionality equation always look like? If I want to make this an equation, I would write that as F equals. Okay, well, it turns out it's M, but we didn't maybe know it was M at first, right? You'd probably learned that before, but pretend you hadn't learned that. It's just some constant times A, right? Where K is the constant of proportionality, and we know from math that the constant of proportionality is just going to end up being the slope, right? This is a direct variation equation. So sure enough, this is just another way of saying force is proportional to acceleration. But what was really interesting about this, and you may have already known this, but to see it I think is something different, is that that constant of proportionality had a real meaning, right? It was the, what? The mass. Yeah, it was the mass of the object, wasn't it, right? And that makes sense. We're going to talk about that. Today's our, Mondays, they're our short days. I kind of,
We should just not have one.
oh, yeah, there you go. I mean, they're already short, so we never get through quite as much as I want to on Mondays. But let's think about this here. What do I want to say with this? I don't know if we'll get far enough to talk about this in terms of Newton's first law, but we've already kind of maybe discussed it a little bit. That's really interesting, that there is some physical quantity that is going to mediate between force and acceleration, and it ends up being the proportionality constant. We're pretty used to it. I mean, we're used to having things that have force, but, we'll talk later on, I think in chapter 8, when we talk about universal gravitation, we'll even maybe take a day or two and talk about really how does that all work? Why is it the way that it is? But that's for a future date. Now we know that's M. The way we did this experiment, remember, we had all of the mass starting off on the cart, and so I could pick a mass off of the cart and hang it. And did that change the mass of the overall system? It didn't, did it? What was the driving force when I picked a mass off of the cart and hung it from the pulley? Okay, the gravitational force acting on that weight, right? Well, and actually, what is the name of the gravitational force? Do you think? Weight. It's actually the weight of that object that was driving the system. We'll get into that more in the future. But gravitational force really is just weight, right? And so, what was if I took a 10-gram mass off of the cart and hung it, was the 10-gram mass, was its weight only acting on the cart then, did we say?
No.
It was acting on the cart and itself, right? Good. So it was still part of the system because it was tied to the cart, right? So would you agree that the mass of the system never varied? It was the same, it wasn't like 2.503, I can't remember what it was, and something like that, right? The mass was the same the whole time though. What would have happened if we had maybe redone the experiment with a slightly different weight? Different mass, I should say. Different total mass. Say I started with a different collection of masses stacked on the cart and redid the whole thing. What would I see? What do you think? Ezra? What do you think? It'd be linear. Yeah. But the slope might be different, right? There was nothing special about the group of masses I put on there, it's just the ones that I grabbed, right? It's still going to have the same basic shape, regardless of which handful of masses I grab. It's still going to be linear, right? But let's just say, for example, that we got maybe this collection of data. Okay. In calculus, later in the year, we'll call this a family of curves. Okay. What would that describe? How would that be different than the one that we looked at? Smaller total mass, right? Okay. So that's good. So we've quantified this really well. We now know that F equals MA, where M really just serves the role as the constant of proportionality in our graph. What about the second question? How does acceleration depend on the object being accelerated? So let's say that the object in this case is the cart and masses together forms the object, right? So in the case of the blue line, we had a certain set of masses grouped together. In the case of the red line, we had a different set of masses grouped together, right? What did we notice about the accelerations, or about the masses and the accelerations? What do you think?
The greater the mass, like the more force required to accelerate.
Okay, yeah. So what if? So what if we took the same driving force? So we hung the same mass over the pulley. What would that look like on our graph, by the way? If the driving force were the same, how could I be comparing those two trajectories there? The blue and the red, those two lines. How could I make a comparison of those two experiments when the driving force was the same? So in other words, I might have started in the blue case versus the red case. I started with a different bunch of masses on the cart, but let's say in each case I picked up a 20-gram mass and hung it. What's that? How could I make that direct comparison on that graph? If the force is equal, what about those two lines would have to be the same? Say it again. Well, okay, they intersect at the origin, but if I just wanna make a comparison, and then maybe this will help. What I wanna compare here is, what's the acceleration gonna be if the driving force, in each case, what would I find out my acceleration was if the driving force was, who knows, some number of newtons, 1.3 newtons. So if the force is the same, what would a constant force look like on that graph? A horizontal line, wouldn't it, right? So wouldn't I really just be doing this? If I did something like, let's say we wanted the force to be right there, pretend that's 1.3 newtons, whatever, who knows if that's the one that we want or not. But if that's the constant force, I've got an intersection there and an intersection there. What do the ordered pairs of these points even represent? Like if I take this ordered pair right there, for example, what are the coordinates? What do they mean? What's the x coordinate? Acceleration. And the y coordinate is force. So would you agree that both of those 2 points have the same y coordinate? So the force acting on them is the same, right? What do you notice about the x coordinate of the blue line versus the red line? They're different. Which one's larger? The red one. That makes sense, doesn't it? Right? Doesn't that make sense? If I have the same force, but different masses, I should expect different accelerations, right? You told me that the red line represented a smaller mass. How come? Okay, because the slope is smaller, right? Good, because the slope corresponded to mass, didn't it? So in the red case, we had a smaller mass, but a larger acceleration, right? That makes sense. That jives with what we'd expect to happen, isn't it? Doesn't it, right? So then I ask again, how does acceleration depend on the object being accelerated? I'm going to get more acceleration for what kind of object? Smaller, meaning smaller mass, right? Okay, so let's go back to our previous, I asked this question a bunch of times. We talked about a bowling ball and a marble made of the same materials. If I drop them, they hit the ground at the same time, right? So let's have a good old-fashioned debate here. Mr. Johnson would be proud of us. Let's have a little debate where let's divide the room right here. You two can decide with them, how about it? So we even things out a little bit. So this half, your job in the debate, and remember in a debate, you have to be able to argue a topic even if you don't agree with it, right? So your job is to tell me why I should expect the marble to get to the ground first. Okay, what advantage it has that should mean it gets to the ground first. Now, you folks are going to argue the side of the bowling ball. Why should the bowling ball win? Right? What's the bowling ball got going for it that means it should get to the ground first? We all know they get there at the same time, but debate on. So take 30 seconds.
You have less resistance.
Okay, real quick, I'll just add one other thing to simplify this a little bit. Let's assume that we're doing this in a vacuum, so there's no effects of air or anything.
You just took our voice away.
No, okay, so I want to. We really don't need to mess with the air resistance. It really has nothing to do with it.
Well, you just took our voice away.
I'll restart the clock though. 30 more seconds.
Stop moving stuff. You guys are going. Let's have less stuff. Does that do anything? No, because air.
Yes,
Am I allowed to ask an off-topic question, kind of?
sure, of
Okay,
course.
okay, so, this is really weird, but when I'm skiing with my brother, and he's bigger than me, he always gets down to the bottom
That's a
faster.
great question.
And I wanna know
Wanna know why?
why this is this, like,
It's
the
very,
same.
it's, okay, yeah, it's a great question.
Okay.
Yeah. Hold that thought, we'll get to that.
Okay.
That's a good
I was
question.
gonna say,
I was gonna
I was ready for you.
Not the velocity so much.
It takes less like gravitational pull to make it go. Like there's not as much action on gravity.
I was
Yeah.
picking up
So like
like most of the boards because.
it just
like,
kind of just like plant,
Except for my.
even though like
If
you
I
drop
stand up, all the weight.
surface area.
The weight is.
Wait.
It just
Okay, let's talk about this.
no.
Let's talk about this. So, look, Nathan, I'll give you spokesperson for your team here. So why should the bowling ball win?
Because it has more mass.
Okay, it has more, okay, but now, okay, change one word. It has more weight. Okay, which means same thing as force, right? And we'll talk more about this later, but let's just get this out there right now real quick, because it comes up in this conversation. Gravitational force, it's just weight, right? That's all it is, right? So that it has more force acting on it. Good, it has more gravitational force. I'm convinced. You got me. Bowling ball's gonna win.
Yeah, they have us convinced too.
Uh-oh. Okay, so what about over here? So why should the marble win? I'll let you take this in one of two ways. You can either tell me what disadvantage the bowling ball has, or what advantage the marble has. The bowling ball's advantage was there's more force acting on it. Sure. Right, absolutely.
Ours was before you took the air away was that the bowling ball had more surface area. But then you took the air away, so we did lost our point.
Uh-oh.
So we didn't know.
Okay, so what's I'll give you maybe a little hint. So the marble, it doesn't have as much force acting. Things don't look good. But it does have an advantage due to its small size maybe.
Yeah.
What's that?
We tried.
What do you think? Why is that good? If it's trying to win a race to the ground.
Just take air out of it.
But even without the air doesn't have any impact on it. Why would that be good?
Look at the line.
Okay, on the graph, let's see.
Which
one? Okay, so look at this. Look at the horizontal green line. We found that if the driving force were the same, right? If the force acting on the two objects were the same, that the red one would have won the race, wouldn't it? Because look, we got more acceleration than we got for the blue one. How come?
It's mass.
Because what about its mass?
It's smaller.
Ah, so smaller mass means it's easier to accelerate. Oh, okay. Whereas that big clumsy bowling ball still has all that mass it's got to get going, right? So now I'm convinced about the marble.
Okay.
Marble's definitely
Yeah,
because
we're
it's
convinced too.
the marble is very easy to accelerate,
It's like
right?
pushing like a boat or pushing a car.
Exactly. It's easy, right? Okay, so both compelling arguments. In the end, it turns out it's a wash, right? The two objects get to the ground at the same time. So the advantage the bowling ball has, by virtue of its very large force acting on it, is exactly counteracted by its disadvantage of having so much extra mass to accelerate, right? Okay, good, so, yeah. All right,
Oh, the skiing one.
the skiing one. Okay, we're getting to that. That's coming up. Hold that thought, because we'll get there very very shortly, I think. So what about thinking about these forces then? Let's do a little imaginary experiment here. We do this a lot. So let's say that I've got a bowling ball with a mass of, I don't know, 10 kilograms out in deep outer space, no gravity anyplace. Now I'm going to take my trusty little spring scale here, which is nothing more than just kind of a glorified rubber band, right? But the thing about this run is it tells me when I stretch the rubber band what the force is. We could accomplish the same thing with a rubber band, we just don't know what the force is, otherwise it's the same. So let's say I hook this thing up to the bowling ball, and I'm going to pull this thing so that it reads 3 newtons of force, just arbitrarily. What do you think is going to happen if you're watching this from a stationary perspective relative to the bowling ball? What are you going to notice happen to the bowling ball when I do this? What's it going to do? It's not a trick question. Okay, so it's going to move in which direction? Yeah, towards the direction I pull, right? And what's the movement going to look like? It starts at rest and it, what? It accelerates. Yeah, no big deal, right? Okay, so is that different than if I hook it to this side of the bowling ball and I pull it this way? Well, I mean, it's a little different. You see something different happen, aren't you? Because now the bowling ball is going to go that way, right? Okay, so then you tell me, is force a scalar or a vector quantity? Remember what's, real quick, somebody remind us what scalar means?
Wait,
It's only numbers.
Oh, say it again? No, you're on the right track.
Only can be positive, I said that.
Okay, well, scalars might be able to be negative too. The ones we deal with oftentimes are only positive, but,
I wrote this wrong then.
say it again?
Scalars just have magnitude.
Just have magnitude, so just numbers.
yeah.
There we go, okay. So scalar, just a number, like for example, temperature, right? Temperature would be something, if we talk about the temperature in the room, we don't need a direction there, all we need is just a number, right? Vectors have a magnitude and a direction. So it makes sense then, doesn't it, that force is what? It's gotta be a vector, doesn't it, right? It definitely, there was a direction. When I pulled it this way, I got a different result than pulling it this way, right? So let's represent that. So if here is my, let's see, I'll be fancy here. I won't be too fancy. I won't take time, but I'll be a little fancy. Let's go like this. So here's my bowling ball. Okay, and here's going to be my. We'll make it a rubber band, so I don't have to draw anything complicated, right? So here's my rubber band that's being attached right there, and I'm going to stretch the rubber band in that direction, right? How could I represent that as a vector? What's the only thing I'm really missing in this picture, I guess, to make it a vector? Sure, but maybe just like that. Just make it an arrow. Voila, now it's a vector, isn't it, right? Remember, arrows represent vectors perfectly because the length of the arrow represents the magnitude and the direction of the arrow represents the direction, right? So let's just say there's my 3 Newton force. Okay, what happens if I hook another rubber band to the same bowling ball and now I'm going to pull on both of those with a 3 Newton force? What's going to be different? Just anticipate here. And you've done enough physics experimentation in your everyday lives. It's called living, playing, and that. What's going to happen if I pull with 2 rubber bands instead of 1? What's the difference going to be in the picture, in the movie? Okay, we're going to get twice the acceleration. Agreed, it's going to accelerate more with a greater magnitude. Okay, so I could represent that with another arrow maybe, right? I could put the arrow just like that. Okay, another 3 Newton. How do we add vectors though? Tip to tail, right. So it might be better for me to take this picture and instead maybe represent it this way. But instead, I take those two vectors and I add them up tip to tail. Now, they're both pulling in the same direction, aren't they? So they're gonna add up, right? And what's gonna be the overall force that's acting? 6 newtons, right? So I maybe could represent this with a single vector that's that long and has a magnitude of 6 newtons. Okay, let's just say that I called, I wanted to maybe label these originally. So let's say we called the original force, we called that maybe F1. And this one was F2. So there's F1, F2. What do you think we're going to call that one? Yeah, I mean, maybe that's the way we could do it. We could. There's a name we give to this, though. I think you probably even know it, just without knowing it. You know it. What do we call if I take those forces and I combine them in a single force? Okay. I would call it the net force. Okay. Think what the word, that's a great word for it. Think what the word net means. When your parents talk about their net income, what are they talking about? Is it all the money they make? Like if somebody makes, if their salary is for making $100,000 a year, do they take home all that $100,000? No, they don't. That's their gross income, right? Their net income has what taken away? Taxes, Social Security, etc. So the net income is what you actually experience, right? Okay, after all the things that need to be subtracted are taken away. And so in this case, nothing's being subtracted, but the net force ends up being 6 newtons because both of the contributions sum to 6, right? Let's change this a little bit. Let's say now that I'm going to be pulling on this side with 2 3-newton forces. Elijah's going to put a rubber band on the other side, and he's going to pull this way with a 3-newton force. So I could represent that now up here in this picture. I'll make this, his is going to be a green force, how about? So in this picture, we would have drawn it like this. And we'll call this maybe F3. How would we represent it if I'm adding them all up tip to tail? So there was my original force. There's another one added to it, tip to tail. If I want to add a third one, I've got to add that tip to tail also, right? So the tip of the second force, I guess I got these backward. That should be a 2 and that should be a 1 maybe, huh? So the tip of F2 is where the tail of F3 goes, right? And then it's going to go backwards to there. That's F3. And what's the resultant then? What's the net force? Okay, so yeah, it goes positive 6, but it goes back 3. And so the net force would only be, see what I'm getting at here though? Right? It's not anything super profound. But now we just end up with net force is only 3 newtons. Now we're starting off in this chapter, we're going to get kind of a warm-up chapter here dealing with forces, where we're only going to deal with forces that are acting on a line. Just like we did with kinematics, right? First we dealt with kinematics on a line, and then we dealt with kinematics in 2 dimensions, right? We looked at maybe winds that were pushing a plane to the side, you remember all that stuff, right? So we'll get there. Do you see even right now maybe where coming up with this idea of a net force and adding vectors tip to tail is going to be very much like what we did before, right? There's maybe one other simplification, boy, we're out of time. There's maybe one other simplification that we could make here. Did I really have to draw the bowling ball? I didn't really need that to be a bowling ball, did I? The bowling ball was excessive, right? If it were a more complicated shape, I certainly would not have wanted to have drawn this. What I could have maybe done instead was just made that a point, right? And that's what we call a free body diagram in physics. And And that's a much easier, more compact way to write this. If I did have some forces that were acting maybe not along that line, I could have added them off to the side like this, right? Maybe we had a 5 Newton force acting there, right? And if I added those tip to tail, if I took that force and I slid it over this way, right? I could have then found the resultant force vector or the net force vector using trig like we did before, right? Make sense? Okay. See where we're going with this maybe? All right. Well, I didn't get to do my fancy demonstration. We'll do that on Tuesday. How about instead? But the assignment is up, right? Didn't I put up the first chapter 6 assignment? Have you had a chance to look at that at all? Okay, start looking at it. It's the first one. It's on the website. Look at that. We'll add to it a little bit more here, and maybe we'll grade those like Thursday and Friday this week. Sound good? All right. Oh, I didn't get to answer your skiing question, but it's coming up. It's a great question.
Thank you.
It's a very good question,
I just really want to know.
and you will know.
Good, because I always lose.
You will know. We could even talk about how you could win. That could be one of our
Well,
class
like, I
projects.
literally like talk like this, and you just look next to me, and I'm like, you know, God.
You're unfortunately, you're probably always going to lose that one, but you have some other advantages.
I do.
There's some ways we could alter the course in a way that might allow you to win.
Okay.
We'll talk about that.